So hopefully you're in the right place. This is a talk about beer. Yeah? Great. Okay. I'll try to not run over so you can go and drink some beer. So I want to start with a little sort of prologue about like what motivates this work, which is all sort of done outside of my day job, though using tools from my day job. So this is my nightmare, and the reason why it's my nightmare, it's a lovely pub. So I should preface by saying that I live in London, though I'm from the US. So if I use strange words, that's why. So this is a nice pub that's not too far from where I work. The problem with it, though, and the reason why it is a horrific dystopian vision of drinking, is that the taps there are the only way that you can make a decision about what beer you should have. So, and they rotate their beer offerings every couple of days. So you've got something like 20 beers, and the information you use to make a decision as a consumer is a little label like this. And this picture is a sort of historic low turnout for this pub. Usually it's like 3 rows deep, so you can barely see the place, never mind actually work out what you should be drinking. So in contrast to this, here is my favorite menu of all time from a unfortunately now out of business pub that was about a mile away from that first place that we were looking at. And don't worry too much about reading it, but the point here is that there's a bunch of information that you can see and use to make a decision. So there's like a sentence that describes what the beer is, there's some information about the ABV, a few other bits of metadata, and like a price point and how big the sort of decided serving size for that particular beer is. So what I want to do is think about ways that we, as people who process data and mine things from the web, can automate the transition from one of those terrible states to the much better and easier for consumers to exist in state. And so that leads me to this talk, which is really about sucking up lots of data and producing a nice summary of that data where you can use to make meaningful choices as a consumer that has something to do and needs to get on with it. Fine, okay, so really then this talk is about 2 distinct things. The first is the domain, beer. So lots and lots of beers, and in fact the volume of beer and the fact that you, as someone who is wandering to a bar, you're gonna have maybe 1 or 2 decision points. Maybe more, but at that point it probably doesn't matter, right? So that's really, I think, a critical thing to keep in mind when you're thinking about this, in contrast to consumer choice ideas in other domains, where maybe if you're listening to music, you can sort of go through a bunch of songs over and over again in a single session, or if you're on Netflix, you can sort of bail from your film and try another one, or whatever. There's lots of iteration that's possible in a lot of other consumer choice situations that doesn't exist in beer. So there's a high price of failure, right? If you pick 2 beers and you realize you made a terrible choice, by the time you're through that beer, that was sort of it for your choices. So the other thing is, of course, just volumes of data. Lots and lots of text, tremendous amounts of text, even more text, and then some more text. So the thing that I think is worth keeping in mind here is that both of these things generalize. So as I sort of hinted at, while beer is distinct in sort of choice penalties and things like this, a lot of the ideas can be applied to other sort of consumer choice domains, music, film, certainly other food, drink kind of situations, but also that the document summarization ideas, documents are an abstraction idea. So we're going to use documents in a literal sense. We have a piece of text that feels like a document when you look at it in the sort of colloquial sense of a document, but it is just a group that is semantically meaningful of objects, right? So people have used these sorts of methods to do screwy things with, say, PCM audio and things like this. So I just keep in the back of your head that a lot of the sort of things that we're doing, if we change the sort of front and back, the pre-processing and the presentation layer, can apply to a world of different kinds of data streams. The other thing is that this talk is informal. I'm going to talk about a lot of math. If you really want to know more about LDA, I really hope you were sitting in your very seat about 25 minutes ago. Tim, the lovely guy who just spoke before me, gave a really good sort of generative exploration of what LDA is. There's lots of other resources on that. And some of the other ideas that we're going to talk about. We're going to spend very little time on the mathematical models and a lot more on the sort of what you do with them and how you can get your data in a place where it will be coherent through the model. Okay, so with that in mind, let's talk about beer for a couple of minutes, because that's the domain we're interested in, and so it's important, I think, for everyone to have some kind of overview about what we're dealing with here. So beer really is just 4 ingredients. So you've got water, which is 90% of beer, and makes a great deal of difference. The sort of mineral contents inside of the water, all this sort of thing will have a big impact on things. You've got malt. Malt here, sorry, I forgot the question. Can I ask, how many of you have ever made beer in your house? Okay, great. Bias is in that direction. Okay, so malt is cereal grains, right? Everything that you make bread with, you can make beer with. The classic ones are barley, which is the principal one that you make beer out of. Also wheat. You can make beer out of corn, though you probably shouldn't. You can make beer out of rye. That's quite nice sometimes. Also, like more exotic grains get used when they're malted. Sorghum, for instance, which is a grain from Africa. There's a list. Anything you can sort of extract starches from that is a grass seed, you can theoretically make beer out of, though some obviously work better than others. Malting is simply a process of tricking that seed into thinking that it's a good time to turn into a plant. So like what we've done is through heat and water said like, hey grass seed, it's time for you to turn into a blade of grass. And then right when it's about to do it, you burn it. And so what you've done is you've converted this like starch reservoir into a pile of sugar. And the pile of sugar in later parts of the process turns into alcohol. And that's how the beer works. So hops are the sort of, in a lot of like modern, especially American craft beer, the hops are the thing. Hops are an herb. They provide bitterness to sort of complement other things going on in a beer. They're very closely related to marijuana, so they can be kind of mellow. They have a lot of interesting flavors that we will see when we start extracting the topics from our documents, things like sort of pine smells, also big citrus notes, stuff like this. But they're very oily, they're very bitter, and it's where everything that is not sweetness and booze and body come from in the beer. The other thing is yeast. Yeast is a lovely single cellular organism, and it does all the work. So it takes all the sugar, it eats the sugar, it excretes alcohol. So when you drink any alcoholic beverage, you are drinking the excrement of yeast. It is delicious. So there are 4 steps. I've kind of hinted at them through the ingredients. So you mash things. So you take all your grass seeds and you soak them in some hot water, and that gets everything going. So that converts the latent energy into a useful form for the yeast. Once you've done that, that takes a little time, then you boil it. The boiling does a couple of things. It's where you add the hops that impart bitterness, so there's a chemical reaction that converts the oils that exist in the hops to something that is perceived as bitter. It also breaks down some proteins, although more of that happens a little later as well. And then once you've boiled things, you add the yeast. The yeast does its work. This takes a few days. It's called fermenting. It's lovely. It smells really good. And then you package it. After all that's done, you stick it in a bottle, or you stick it in a keg, or you stick it in a cask if you're in the sort of place where casks are a thing. And that's where the carbonation gets, well, not added because it was there anyway, but that's where it gets kept so that it can impart a certain sort of flavor to your beer. So you've got basically 4 ingredient classes and then 4 big steps for process. And from those reasonably small things, you have a tremendous variety of beers. And so the thing about beer is that there are a lot of people who are very obsessed with beer. And I mean, like, people that make my obsession levels look mild and amateur. And so here what we have is a couple of people who are judging volumes of beer. This is something I do on the weekends also, I should say. So they've got, this is a best in show judging competition, so they've got little like 2-ounce things of about 25 different beers that all won their little category, and they're going through them, and they're sniffing them, and they're rolling them around in their mouth, and they're writing like 3 pages of text about them, right? And then grading them. So okay, that's fine, but they're doing that with a pencil on a piece of paper, and that's not actually useful for our sort of motivating goal from earlier on in the talk. So I'm going to spend a little bit of time talking about a website called Rate Beer. It is not the only place where this sort of behavior goes on, but what this basically is a website for the kind of people who spend their weekends judging beer and thinking that's a good use of their time. Rate Beer has, the kind of metadata that you would expect about beer, ABV, the brewer that makes it, these sorts of things. And also up here you can see, so in a way that's very, Netflix-ish, this kind of thing, lots of modern consumer websites, there's ratings, and it compiles the ratings. It does a sensible bit of statistics where it actually gives users of the website more value if they've been contributing for a long time. So that thing that says weighted average up on the screen, I don't know if you can see it from way in the back, that actually does not equally weight and average everyone. It sort of works out if you're a good user of the website and then binds things together. But actually that's not really what we care about here, although there's a wealth of data that's interesting. What we actually care about is if you scroll down the page on a rate beer listing, you get this big block of text, or at least big by sort of user-generated content review kind of sites. And because of a bunch of UI conventions on RateBeer, it really encourages you to take the thing you're rating and sit down at a table and have a think and write like 200 words. And so people have done this, lots and lots and lots of people. So, and in fact, for that particular beer, there's about 2,000 reviews, and they're all about that volume. So you've got 2 to 4 sentences from a bunch of different users, and in addition to the ratings, you've got this big descriptive text. So let's poke a little bit more at another beer from RateBeer. This is the Kernel Export Stout, which is from a brewery that's not far from where I live. It's very lovely dark beer that, in spite of being called a stout, actually has a pretty big hop aroma, which makes it kind of interesting because it's a little bit of a sort of push against the style conventions for what a stout can be expected to taste like. And it also doesn't get around very much. So almost everyone who reviews it either is a beer nerd who sort of like pull some favors and get someone to bring them one, or lives in the local area because they don't export this beer. So we can see the reviews here. I'll read a couple. So the first one says, treacle-like, viscous, thick, a dark brown or black cream brown head. Can't think of much to improve here. Bitter and sweet and mineral all in one perfect harmony, right? So he clearly liked that beer. You know, there's a bunch of other things. So we can sort of pick out some flavor notes. There's a big aroma, some ashiness, dark chocolate notes, strong coffee, right? That gives you kind of an idea of the idea of the beer. So if we take that text and we just extract the text out and we ignore all the context, we sort of get something like this. But actually, what we have is something like this. Now, in the back, that might just look like white fuzz. That's every single piece of text that was written about this beer by everyone from RateBeer. So clearly, that's not quite enough. And in general, in fact, lots of people write lots of things about beer. So if what I want is a quick and easy consumer decision kind of tool, we need to do something with this. We can't just simply sort of, you know, pull out our phone and go to RateBeer and go through each of the 20 beers and read 2,000 reviews and make it. I mean, that's not going to work. Okay, so text processing. Let's talk about text processing. So in particular, we're going to look at the sort of broad natural language processing ideas, which is what NLP stands for. And we're really interested in one particular field within NLP, which is called document summarization. And again, I document is in quotes here because we're talking about text, but it doesn't have to be text, right? Anything you can represent as a stream of data can be a document that can be summarized through these methods. So one of the things that's really general in almost any kind of data from the wild NLP process, which certainly means anything where you're gathering all your data from the web, is that you're going to spend 90% of your time, 95% of your time trying to pre-process your data. So before we do all of the fancy statistics that everyone's been talking about, we have to make sure that the data we're giving to our statistical models makes any kind of sense, is normalized in any kind of fashion, has weird character encoding problems pulled out, that it doesn't have errant HTML tags. There's all kinds of crap, and it's littering our data, and we need to get rid of it. So the first step is something called tokenization. I suspect this crowd actually knows what tokenization means. Really what tokenization is a really overly considered way of saying that we're going to break on white space and then we're going to lower all of our characters to lowercase, right? Like this, right? So whenever anyone says tokenization, they're just trying to feel fancy and they're just doing this, right? So, or well, mostly. So we can actually be a little bit more sort of savvy than that. We can use a language processing library. Here I'm using NLTK. Later I'll use another package called Spacey. They're both doing roughly the same kind of thing. So here what we have is we have a tokenizer that understands punctuation and a few other things and is breaking on all the ways that words are separated in written language and throwing out all those intermediary characters. So what you get is reasonably clean words, and then we're lowering everything because if someone says black at the front of a sentence, we want it to mean the same to our model as black at the beginning or in the middle of the sentence, excuse me. And the reason for that is because, as was discussed in the last talk, we're throwing out all the sequence data, right? So what we're going to end up with in a little while is a bag of words representation, just word counts for our documents, right? So we can be even a little bit more savvy. We can get rid of words that are useless in our understanding of things. We can get rid of punctuation, etc. You can spend quite a lot of time on this, and actually this is one of the places where you can get pretty domain specific. So in this case, because what we really care about here is descriptors of things. So really, in this application, we're using reviews as a proxy for content description, right? So what we want here is a collection of terms that describe a thing in physical space. So what we're going to do here, what this slightly messy list comprehension is tokenizing and then using part of speech analysis, which tells you if something is a noun or a past participle or an adjective or an adverb, and it's throwing out everything that is not strictly a noun or an adjective. Because since what we're doing here ultimately is proxy descriptive terms, we don't care about thes and ands and always and very. We care about black and brown and malt and hop, right? And so we're going to end up throwing out about half of our words from our corpus, but what we're left with is the part of the corpus that matters for this kind of thing. And in fact, because we're doing this sort of bag of words goes from a weakness to a strength, because really what we want is counts of descriptive words, right? And that's all we're trying to do here. So this is, I think, the reason why I'm sort of picking at this is because what this is it's applying domain knowledge to the statistical process in a way that makes the statistical process have to do less work, right? And I think that's going to yield some success. Okay, so we have all of this pre-processing. Now what are we going to do with it? So the simplest way that we can take all of these piles of words and counts and give them some kind of meaning is something called TF-IDF. So I've given this talk to beer nerds before, and I suspect it's going to be on its head. How many of you have ever done something with TF-IDF? Never mind, no. Oh, great, it's 100%. Super. Okay, so we'll fly through this part then. Okay, so TF-IDF is term frequency, inverse document frequency. Here's a little model of it. Basically, you count up how many documents a word appears in, then you take each individual document and you do a count for the words there. You get a little fractional weighting. If we do a little example in beer, we'll go back to our export stout. And so we have this big volume of words, right? The big volume of words is too much reading. So what we can do is through TF-IDF and our pre-process, we'll end up with some words and some weights. So similarly to sort of the particular little sample that I took and read at you, we've got coffee as the highest weighted word by this TF-IDF process, then chocolate, then black, dark, licorice, espresso, cocoa, brown, bitter, smoke, whatever. So I don't know about everyone in the audience, but whenever I see sort of TF-IDF processed words, I always sort of get a flashback to like days gone, late 90s, and I make word clouds, right? And so here we have the sort of top 10 weighted terms in a word cloud, which I've just noticed like there every now and again you see this sort of like, ooh, look, I can make word clouds out of collections of text. And there was one going around Twitter, and I'm like, is it 1997? I don't understand. We need to move on. But anyway, so this is a reasonable way to represent things, I suppose. But the problem here is that the computer is really not clever. So you and I, as humans, we can sort of work out that some of these words kind of mean the same thing. They correlate in certain ways. They get used to describe the same kinds of things. If we look at this word cloud here, what we have is we have overlapping terms, right? So we've got this little note of espresso, but also this coffee. We have black and dark and brown that are all describing a certain sort of quadrant of color. We have cocoa and chocolate. Okay, so what can we do? So we can do topic modeling, right? Sorry, so I live in Britain. We can do topic modeling. I have to remember what side of the Atlantic I'm on. Okay, so topic modeling. Who in this room wasn't here for the talk beforehand? The last talk. It's like half. Okay, so to review, the broad high-level idea of topic modeling is that you have, instead of just describing how likely different words are and how much sort of meaning a word has in a document, which is basically what TF-IDF does, how differentiating a word's usage is for a particular document among a corpus. You have this intervening, which is what we have here. You have this intervening idea where what you want to do is first work out how often words occur together, roughly. Again, this is informal. And then you use that to build this notion of topics. So if you notice that black and dark get used together on a regular basis, then those are probably in the same topic, right? And that's really what the inference models of topics are doing, is they walk through your corpus and they work out how likely words are to occur together-ish, kind of. Okay, so once you've done that, then you do that with all the reviews, right? So you build up this notion of what kind of words are used together notionally in individual documents across your whole corpus of documents, and then that gets you topics. And you can infer them in a few different ways. There's plenty of resources to work about that. If you have if you want to talk to me about ways to infer topics, we can talk about that later. That's outside the scope of the talk. But so if I do this on my beer corpus, you get these sort of topics that are grouped together, and these are topics and the top 5 words in a topic and the probability that they occur given a topic. So we've got, as expected, you've got this grouping of like sort of color and aroma that couple together for sort of chocolate dark kind of beers, and then a similar but not quite the same dark smoky note, and then this one down at the bottom, citrus, hop, grapefruit, orange, pine. For people that drink a bit of craft beer will recognize that as a particular kind of hop aroma that is frequently found in stuff like IPAs. Okay, so topic modeling is an activity. That's the first step. You've got your topics. But then what you're going to do is you're going to describe a document as a mixture of topics instead of directly as a bunch of weights of words like you would do if you're doing TF-IDF. So how do we do that? So we're going to use a process called latent Dirichlet allocation. And latent Dirichlet allocation uses Dirichlet models, which are a statistical abstraction, to find your latent variables. And so if we look at what a Dirichlet is, so a Dirichlet is basically just a discrete probability, and this is how we're going to model both our topics and our documents in LDA. And so here we have some colors, some blocks of color. They have probabilities for being in this document. And so we can notionally think of this idea of if we sort of kick the document, what color is going to come out, right? Is it going to be blue? Is it going to be pink? Is it going to be black or white? And we've got some probabilities for that. Okay, so this is not anything that's that revolutionary, but if we sort of back off to talking about topics and documents, 2 layers, effectively each one of those blocks, instead of having a known color distribution, is a distribution of distributions. And so you sort of emit twice, effectively, right? You've got 2 different layers. Again, this talk is informal. If you wanted some of the math, I hope you were here for the last talk, and feel free to dive into this in depth later. So, okay, so we have made some topics. We've made some documents about some topics. What can that tell us for beer summarization? So let's go back to this kernel export stout. It's pretty nice. We have this massive pile of words. It's too many words. We can't read it. So the export stout has, these are the 4 top topics. And actually, I should step back and point out that one of the things that is very hard to do in topic modeling is display the topic in a way that's coherent and has meaning. So what I'm doing in this talk is following a convention when people talk about topic modeling and just displaying the words that are most prevalent in the topics. But that's actually not necessarily the correct semantic thing to do to explain what a topic's about. So apologies, but anyway, so we have dark, sweet, sort of raisin thing. So this is this idea of like a fruity dark thing. And then we have this other sort of fruit note that's more actually from hops, this fruit, peach, tropical, mango, apricot. That's a hop note. And then another hop note, which is pine, citrus. And then this 4th topic is interesting. This 4th topic is not so much about flavor, but about texture and appearance, right? So this is a beer that's thick. And so it's got good head retention, and it pours well. So they're talking about the texture and the appearance in that 4th topic, right? Okay, so if we think back about the domain, I was talking about how there were 4 sort of prevalent ingredients. Can we find topics that clearly correspond to those ingredients, right? If we think about what this topic modeling process can tell us about our domain. So we've got water, hops, malt, and yeast. And so here's a hops topic. There are a few of them. You saw that in that last description as well. Here's one about malt. So we've got caramel, amber, malt, sweet, copper. Copper is an appearance note, but that's clearly something that's coming from your malt characteristics. So yeast. So does anyone understand in the crowd why I've put banana and clove and bubblegum, which don't necessarily seem like things that have anything to do with microbes, into the yeast category? Does anyone like German wheat beer? Any show of hands? All right. So has anyone ever described what they sort of smell and taste from a German wheat beer as banana or clove? Yeah. Okay. So that comes from the yeast that is used to ferment wheat beers, typically, and there's an interaction that happens with nitrogen. This is not a chemistry conference, I won't get into it, but basically that chemical reaction produces the thing that is perceived in your mouth and then in your brain as clove and banana, and in fact bubblegum as well. And the difference between those 3 flavors has to do with the parts per million that's present in the beer. So it's all just the same chemical because brains are crazy. So banana and clove, which I don't think a lot of people group together psychophysically, are actually from the same chemistry, and it's just a perception issue and a sort of density of that chemistry. So actually, this is a very satisfying thing that these things get grouped together as a topic, because you expect them to come from the same class of beers. So this is a good sort of sanity check in a lot of ways, right? Okay, so and then water. Okay, so what I've put here for water is a little bit, it's a little dubious, but I'm gonna push on it a little bit, and the reason is because what we have here is we're describing the sort of nothingness beers, and we'll cycle back on this a little bit. But when you look at beers that are soft, that are I think in the U.S. there's a term a lawnmower beer, which is great. So this is from where water is most important. So you do not have other things to cover up the softness and mineral character of your water, right? And this is the sort of descriptor you expect-ish, kind of, from here. Okay, so let's talk about the topic of the talk. So great taste, less wordy, or actually, to make the reference slightly more explicit, less filling. So there's been a branding campaign that's gone on for nearly the entire time that I've been alive by a company that ostensibly makes beer. And so what I want to do is see if we can use this tool to better understand what great taste is less filling. So let's look at Miller Lite. So Miller Lite is on rate beer. In spite of its general obsessive nature, it does actually cover pop beer as well. It's not just for indie bands. I mean beer. And so okay, so half of the topic when you're looking at the reviews is white, light, clear, golden, and watery. Now that's the same topic, by the way, that I stuck on for water just a minute ago. So 9% comes from this sort of golden, white, grassy, light, pale, which is a very similar topic. So I ran the topic analysis with 100 topics because it seemed to do about right in terms of topic separation. So one of the ways that you can sort of qualitatively work out topic numbers is by seeing how separate your topics are. This idea that, like, if things are reasonably dispersed across your word space, it's about the right number of topics-ish. Now, these two things overlap clearly, but they're kind of talking about different aspects of the beer, right? One is a little bit more concerned with aroma, and the other one is a little bit more concerned with texture, or in this case, the sort of lack of texture, right? So that grassy note is a big hint about aroma as opposed to texture. Okay, so then we've got another one. This is 7%, and it's like a head description, a little bit of color, and last, we've got a sort of little bit of a flavor note that's kind of maybe backing off our sort of assertions, and that is enough to write it off. The rest of the topics are all much lower. So you've got, again, it's 100 topics. So that's really the bulk of the descriptive character. Okay, so let's have a little epilogue about similarity. So in the abstract of this talk, I said that we could use these methods to actually compare how different beers are, or at least how different the beer reviews about different beers are. Because remember, we're just talking about a proxy here. We're not actually sticking beer in sort of a spectrometer and measuring characteristics of beer directly. Okay, so actually, if I restate this, what I really mean here is that I have the same taste and you've changed your beer menu. So if I know what I liked from your beer menu before, how can I work out, without doing an exhaustive brute force sample, what I like from your list now? So we're going to look at vector space models, which actually is what we've been doing quietly for a lot of these things before, but let's pick at it a little bit. So a vector space model is an idea where you have a bag of words, and what you're going to do is you're going to project that bag of words into an n-dimensional space, where n is your vocabulary in the most direct sense. And you know, there are reasons why we might need to not do that directly, but we'll just sort of keep things simple and talk about it directly first. So if we have a toy example, we have this is all the sentences that are possible in this sort of fictional world. Again, and I did not talk to Tim, who gave the last talk. I didn't know he was also going to use emoji words, but it's quite pleasing to know that he and I seem to be in the same headspace about this. So here there are two words in a whole language. The words are sunglass smiley and sad cat, and that's apparently enough to describe all notions in the universe. And then these three sentences are sort of our corpus, right? So we've got, you know, a sort of 5 smiley, sunglass, 3 cat notion, and down to sort of even and other things. So what we can do in a vector space, here now conveniently, it's almost like I did this on purpose, since there are only 2 words in the whole language, we can just put this on a graph, which is great. So this is a vector space model in a 2-word language with no like crazy projections to get your head around. But this is all vector space models are. You take the words and you just put them on a graph. So, well, this is neat. So I can measure the distance between those points, right? Okay, so in fact, in general, from this graph, from this vector space projection, we can work out that sentence 1 is more similar to sentence 2 than sentence 3, right? Which if we go back and look at them, remember bag of words, it simply just counts, right? And the counts of words in sentences 1 and 2 are more closely aligned than either with sentence 3. Okay, so the reason why we have to do VSM not directly on word counts and on vocabularies directly is something called the curse of dimensionality. Does anyone in the room know what I mean when I talk about curse of dimensionality? Anybody do similarity measurements? Okay, so it's this statistical notion that when you have very, very high dimensional space, everything ends up being very close to everything else. It's a really fun mathematical proof to get your head around. But basically, if you have a 10,000 dimensional space, there's no point in measuring distance because everything is kind of uselessly close to everything else. And so if we have 10,000 words, because we're looking at spoken English, we have to do something before we do this vector space projection, or there's no point in taking distances. So topic models and a few other, there's a bunch of strategies for doing this. Topic models is one, because what we end up with is documents that have 100-dimensional space, which is much better than 10,000 or 100,000 dimensions. So, okay, now practical advice. So I'm from London. I know what beers I like that are available in London, but I'm not in London right now, and I'd like to have some idea of what things I should maybe be questing for from the better craft beer bars in the area. So I can take, and I can answer this question with my data, right? What New York beers, what beers produced in New York are similar to the Kernel Export Stout by this review process? So this is answerable with a vector space model and just a simple geofilter off the metadata that I've collected from Rate Beer, right? And so the code to do this is like 20 lines, right? So this is all the code that we've talked about. This is the pre-process half, and then you build the model. That's the last step down at the bottom, building an LDA model. It's really simple, the pre-process. We're just cutting up all of our data. We're throwing out all the words that are below 2 characters because we assume they're not actually that useful. Otherwise, we're not doing any filtering. And then the sort of business end of things, we build a similarity matrix, which is just simply measuring in that projected 100-dimensional space how far apart using cosine distance points are. And then we're pointing out which place the kernel beer is there. We're measuring the kernel beer's distance from all the other beers in the space. And then we're throwing out the beers that are not produced by a brewery that is based in the state of New York, which is that business that I'm pulling from the SQL database. As an aside, it's 2 SQL calls because this is all in SQLite, and doing the join is actually tremendously slower than working this out in Python, which is, if I cared enough, I could put this in Postgres, but this works. So let's look at that. So these are the 5 beers that won that metric and their similarity scores to the kernel beer. Now, one of the things that I find as someone who spends too much time thinking about beer, kind of fascinating, is that actually a bunch of these beers, especially the first one, are not the same style, but this makes sense because the Kernel Export Stout is quite a bit hoppier than a lot of things that are called stouts. So what you have here is a black IPA, which for people who aren't style nerds is a sort of emergent style that's kind of like a stout or a porter, but maybe not quite as thick and full of hops like you would get in a paler beer. And then you've got a vanilla porter. I don't know what the Krek is doing in this list, but everyone is fallible. Maybe the topics were not quite clean. And then a couple of triples, which are Belgian styles, and not quite the same sort of thing, but a little bit different. And so all of these. In fact, I can pull up some of these beers. We can look at them on Rate Beer. If I quickly go away because I have a couple minutes. So here's the Heartland Black IPA. One of the things that I really like actually about this method of similarity is that it pulls up beers that if I was using a social similarity metric, like through collaborative filtering or something, which of course is possible with this set because we've got lots of ratings, wouldn't get pulled up because these things are just not that popular. So this completely, it ignores both sort of positive negative judgments So you'll find a couple of the beers on that list are like really low down in the rating. They're like a 2, and that kernel beer is quite highly rated, and also like low rating. So this has 9 ratings. If we look at that vanilla porter, it's got 37, a few but not lots. And in fact, this Krek is got 19, which might be why it ended up on there. And then the Omegang is a little bit more popular and also quite well considered. Fine, and that's about it. It's 5:42, so I think I'm about done. So I'll happily take some questions if we have a couple, and thanks a lot.
Could some of the taste come from air, salt, humidity, by the ocean, etc.?
Yes. So do you mean the taste that someone who's tasting a beer gets, or the taste that the brewer sort of gets in the beer?
Could you have put any of the topics under that category as opposed to the 4 that you chose?
Ah, I see. Yes. So that was definitely a qualitative exploration of the topics, and not like a sort of good. So you can do clustering of your topics, and actually like something to do from here that would be a bit more rigorous is to see if there's clusters of topics describing the same kinds of things, which is something you can do. And then what you'd expect to see is some of the topics that talk about certain elements within the beer to cluster together. So like aroma-focused topics or things that are very concerned about malt are going to end up clumped together. Maybe, although I haven't run it. It's possible that things would actually drift by style or by locale. So there's a bunch of other things that can drive word usage, because at some level what we're talking about here is linguistics as much as it's beer, right? So it's entirely reasonable for the data, for instance, to shake out by geography as opposed to by beer style, right? So it doesn't seem unreasonable that people talk about beer in ways that are defined not so much by the beer, but by whether or not they live in New York or Belgium, right? And so that's one possible explanation for some of the deviation, and there are ways to sort of look at that. Clustering is an immediate answer, but there are a few other ways that you could sort of pick that apart as well. Anything else?
So when are we going to get beer similarity as a service?
Oh man, like we can have a talk afterwards. That's something I would love to do. There are, in all seriousness, there are a few like commercial attempts. I think there's still a lot of work to be done in the space. There's a mobile service called Untapped. In addition to Rate Beer, there's another organization called Beer Advocate. Rate Beer and Beer Advocate are the two sort of like old guards in this space. They've had like LAMP stack websites for about 15 years, longer. I think both of them are mid 90s. Untapped is newer and mobile first, but they don't. They're not rigorous with their data, is I think the polite way to put it. So theoretically, they have like a recommendation service. They give you recommended beers right when you've checked in a beer, which is roughly the opposite of when I want someone to help me decide on a beer. And there's a bunch of sort of strange things that happen with that service. And I think there's a lot of potentially empty space in the area. So yeah.
So you made a point to mention that a lot of these techniques generalize well beyond direct NLP applications. So did you have any examples in mind that you could provide?
Sure. So there have been some examples of people using topic modeling to do things like develop distance metrics for playlists. So there's some work. I'm the first author of the work, which is why I know of it. That takes audio thumbnails in sequences and uses sequential distances that are projected down into lower distance spaces using an LDA model, and then measures the distance between those spaces and uses that as a distance metric for playlists of audio. There's also been some work in the same sort of circle that uses tags, so freeform tag text as opposed to prose text, which is another step away in combination with audio to do similar kinds of distance metrics. I've seen some work that uses social network analytics as the first step. So actually what you do is look at features of nodes and graphs, and then from that you use topic model analysis to do dimensional reduction. Basically anywhere where you have too many dimensions and you want quite a few less, and you think there is some semantic intermediary level there's a potential application for topic modeling.
Situations where you have counts of too many things?
Yeah, that's right. Yeah.
Okay, thank you.
Thanks a lot.